Wow. So let's solve some more questions. Ooh. The switch in the circuit moved from A to B at t equals 0. Determine V as a function of time for t greater than 0. Very simple. Very simple. Light work. We've got the same double pole switch. All right. T less than 0, nothing complex here. 40 volts, 20k, 60k. We switch to B. 8k, 160k, 40k. Let's get straight to work. All right. Let's see how we're going to do this. Solving for t less than 0. Solving for t less than 0. Okay. This is the only thing we're going to have. All right. I don't even have to draw it. Recall, this is going to become an open circuit this way. This is going to be in parallel with the 60k. So we're just going to divide 60k. All right. So V0 is the same as voltage to the 60k. We're going to divide that with the 40 volt source. So that's going to be 60k over 60 plus 20, that's 80k. The k's are going to cancel out. Multiply all of this by 40. All right, what does that give us? I believe 40, 42, 30 volts. All right, I don't even have to draw that. So we have our initial voltage. V0 is straight up 20 to 30 volts. We're done with t less than 0. Let's get to where the money is at. For t greater than 0, where do I draw this? Okay. For t greater than 0. Oof, why am I not right? Okay. For t greater than 0. All right, let's look at it. Now we've got, okay, let me take the time to draw this. I'm draw up here. Resistor, minus, plus. Ooh. That was one line. Okay. Minus, plus. We've got our capacitor over here. And then it's 160k ohm resistor. That's a really big resistance. 160k, 40k, 8k, 1/4 microfarads. Again. All right. This is 75 volts. First thing we're going to do, find our Thevenin. Turn this voltage source off, becomes a short circuit. Becomes a short circuit this way. That means 40k is in parallel with 160k, because they'll end up sharing this node, since it's a short circuit, and this node together. They're in parallel. How do we find parallel resistance? So the equivalent between 160 and 40, 160k in parallel 40, is going to be, remember, product over sum. Yeah, product over their sum. 160. Pardon me. All right. 160k times 40 all over 200k, and that gave us 32k. All right, so for us to redraw this, we end up with 32k, 8k, 1/4 microfarads. I just want to illustrate what I was doing with the resistors in parallel. This is not our Thevenin's. We're on the process. Now we can see that, all right, 8 and 32k in series. Adding that up gives us nice and cleanly 40k ohms. So we know that our Thevenin's is going to be 40 kilo ohms, meaning our time constant, tau, going to be RC. That's 40k, 40 times 10 to the 3, times our resistance is 1/4. A micro is 10 to the minus 6. Okay? What does that give us? This is 10 times 10 to minus 3. That should be 10 to the minus 2. So our time constant, tau, is 0.01 seconds. You can see we're stacking up 0.01 seconds. You can see we're stacking up the things you need to solve the problem. All right. So now what's left? V infinity. V infinity. What is going to happen now? Let me draw the circuits for clarity's sake. For t tending to infinity. What do we have here? A capacitor becomes open, alright? Open says me resistor, upside down source. Close everyone. 160k, 40, and I'm assuming this is 8. This is V infinity. What happens here? V infinity, this is an open circuit. Okay, which means once current enters this loop, it is not going to be able to make it back to the circuit, meaning that current does not enter this loop at all. There is no current in the loop with an open circuit. There is no current in the loop with an open circuit, meaning this guy, this 8 kilo ohms resistor here, receives no current at all and is practically not a member of the circuit, meaning that V infinity is still in parallel with 160k. I really hope that that's clear. There is no current through 8 kilo ohms because this is an open circuit, meaning that this has no effect. This is null, is redundant. All right, meaning V infinity is still going to be the same as 160k. So I believe this is 75. Okay, this is 75 volts. So let's divide with 160. So V infinity is V60, V160. I haven't forgot. So that's 160k. The k is cancelled out. 160 over 160 plus 40, that's 200. Multiply that by 75, giving us 60 volts. All right. Now let's be careful here. Look at the question. We're given the polarity of capacitor to be positive here, negative here. The current leaving this 75 volt source is, this is reversed. We have negative then positive. This is flowing in a direction opposite to what we're used to. This is plus up, minus down. So current is going to flow this way, but this current is going to flow backwards, meaning that our V infinity is going to be minus 60 volts, since our source is set up in a negative direction, a negative polarity. All right, so V infinity is 60 volts, minus 60 volts. Pardon me, and that's all we need to solve our question. Whoa, this has been really tasking. All right, so how do I keep making this error? Let's close my rectangles. Okay. So V as a function of time, I hope you're excited, is V infinity plus V naught minus V infinity e to the minus t over the time constant tau, all in volts. What's V infinity? Minus 60 volts. So that's minus 60 plus V naught is 30 minus, be careful with this, minus first, then V infinity as minus 60 volts e to the minus t over 0.01. I believe that's going to be 100 when you take it up, all in volts. All right, so what do we got? V as a function of time is going to be minus 60 plus 90 e to the minus 100 time volts. Simple and squash. All right, guys, one question left. Let's get to Let's get to work. Find V of t for t greater than 0, assuming the switch has been open for a long time and closes at t equals 0. Let's ask ourselves what's happening here. Find voltage as a function of time for t greater than 0. So we are not ending up with a piecewise function since we're asked for only t greater than 0. If we're asked to solve for all time, okay, then our piecewise function is going to look something like V of t is going to equal V naught for t less than 0. Pardon me. For t less than 0. And V as a function of time for t greater than or equal to 0. Okay, this is only when you're asked to solve for all time. But that's not what we're told to do here. We're told to solve for t greater than 0. So you've got to be careful with that. Prepare yourself mentally for the question. Find V of t for t greater than 0, assuming the switch has been open for a long time and closed at t equals 0. Meaning, for t less than 0, this guy is open. This is the only thing we're dealing with in our circuits. Source, resistor, capacitor. Once this closes, we have a very nice, funny-looking setup. I saved this question for last. It's a setup you might not usually encounter. And you may panic since you have two normal sources active at t greater than 0. So what's going to happen? What are we going to do? So let's get to work. This is the final question. For t less than 0, do I have to draw this? For t less than 0, no, for old time, for fun's sake, let's do this. No. Okay, I'm sorry. Let's draw this. Plus minus 2 ohms, a third of a farad, and we close our circuit. 1/3 farads, plus or minus volts, 2 ohms, 10 volts. Alright, and then we asked, what is V0? What is the initial voltage across the capacitor? Remember, we're dealing with t less than 0, a capacitor becomes an open circuit. Alright, meaning that, resistor, boom, bap, open circuits. Okay, V0. What does an open circuit mean? This means that current cannot flow through this 2 ohms resistor. Because if ideally you were to draw a current flow, right, leaving our source, passing through here, is to get to this gap and not be able to continue. Alright, meaning if you were to let that happen, current will just leave, and pile up. And that's a violation of energy, violation of current law, violation of, a lot of stuff. So that means current, noticing that there's a gap here, ceases to leave the source. Okay, so current doesn't leave the source at all, meaning there's no current through this guy, and V0 is exactly 10 volts. It's exactly 10 volts. Alright, so that's what we have for t less than 0. V0 is exactly 10 volts. Solving for the more fun stuff. T greater than 0. Okay, I believe this will. Ooh, okay. Okay. And we write this a bit clearer. For t greater than 0, okay, I want to withdraw the circuits on top. We close the switch closes. Okay, so we end up with something like plus minus, this is a source, minus plus. Okay, 5 volts, 10 volts. I will use this drawing. So this is for t, once switching happens, for t greater than or for t equals 0, practicing. Okay, a capacitor becomes active because it starts discharging. Alright, to find, remember, what are we looking for now? Thevenin's resistance. Okay, so that's going to be, because we turn off our sources, this becomes short. So this is in parallel with 2 ohms and 6 ohms. Okay, so we're just going to find the equivalent of 2 and 6 ohms. That is exactly our Thevenin. So our Thevenin's is going to be 2 ohms in parallel with 6. That's going to be 2 times 6 over 2 plus 6, 12 over 8. Our Thevenin's is equal to 1.5, 3 over 2, right? Yeah. 1.5 ohms. You don't stop there. You find your time constant. Tau is RC. Okay. What's our capacitance? 1/3. Okay. Farads. That's 1/2 times 1.5. 0.5 seconds. Simple and short. Tau is, 0.5 seconds. So you can see solving step response circuits isn't particularly difficult. You've just got to be able to look at it, make a decision, analyze, withdraw your circuits, and find what's needed. Okay, so we're done with t equals 0. Now we need to find our V infinity, infinitely far into the future. All right, what happens there? This is very, very cool. So for time tends to infinity, how do we find V infinity with two sources in our circuits? The capacitor becomes an open circuit. Okay, so let's redraw that for convenience. Capacitor becomes an open circuit. Okay, and this is V infinity. How do we do that? How do we do that? Very interesting question. The way I found to solve it, one way I did, there's a way I did which you could source transform this left side, source transform the right side, find the equivalent, source transform them back up, add the current sources, and you end up with a simple source resistor capacitor circuit. And I did that and it worked. But let me introduce you to something that can also help, which is using nodal analysis. Okay, which is like working backwards from nodal analysis to find V infinity with a complex setup like this. So the voltage at this point is going to be V. All right, the voltage at this point, okay, since we're doing nodal analysis, set up our ground. This is our ground, 0 volts. We have a 0 volts as our ground. 0 volts as our ground. This is V. The voltage at this point is 10. Okay, because you have 10 here, down here. Oh, is this correct? Okay, and this is -5 because of the way the source is acting. So let's say we wanted to perform nodal analysis here. So we had current flowing this way, current through 2, we had current flowing this way, current through 6, but we wouldn't have current flowing through even infinity, remember, because of the open circuit. So that means I2 is going to equal I6. Going to equal I6. Okay, what does that mean? Remember, recall I is V over R, so you take the voltage at the first node, minus it from the voltage at the final, that's in the direction of the current flow. The current will have a tail and a head. V tail minus V head all over resistance. V tail minus V head all over resistance. Let's get to work. So that's, okay, this is 0 volts at the ground. If this is minus -5, it still checks out. So for I2, the voltage at the tail is what? 10. The voltage at the head is what? V. The resistance is what? 2. For I6, V tail is what? V. V head is -5. The resistance is what? 6. Multiply through by 6. Let's get to work. That's 3 here. So that's 30. Minus 3 volts is equal, this clears out completely. V plus 5. Solve this simply. Take 5 to the other side. 25. I should write better. 25 is equal to 4V. V is equal to 25 over 4. V infinity. V. Okay, let's slow down. So V is equal to 6.25 volts. So V infinity is going to be the V at this top minus V at ground. Since this is our reference node, this is 0 volts. This becomes 0. So it's 6.25 minus 0. That's 6.25. So V infinity is 6.25 volts. Which is a really cool and nice way to work around it. The current isn't the point of the whole thing, because you can see we'd even evaluate current at the end of the day. But we're using the fact that since we have expressions with V on both sides, we can solve for V and end up, tricking KCL into giving us the voltage, V infinity. So to wrap everything up, let's write our tools. V naught was, trying to remember, 10 volts. Our time constant was 0.5 seconds. And our V infinity was 6.25 volts. This is all we need. Recall, finally, I hope we're happy. V as a function of time is V infinity plus, open a bracket, V naught minus V infinity e to the minus t over time constant all in volts. V as a function of time is going to be plus V infinity 6.25 volts. That's 6.25. All right, straight. So that's 6.25 plus V naught is what? 10 minus V infinity 6.25 e to the minus t divided by 0.5 volts. Opening at this point, once you see t as 0.5 volts, carry it up, make it minus 2t. So V as a function of time is going to be 6.25 plus 3.75 e to the minus 2t volts. So that's it. 4 different questions on step response RC circuits. I really hope this was helpful. If you have any questions, any points you feel I didn't explain well, please feel free to leave them down in the comments. Thank you.